We all know that communication is very important. All form of communication consists of two parties at the given time, the transmitter and the receiver. Now, face-to-face communication presents this particular challenge. If you try to tell me something, you better be within my hearing distance. Unless, of course, I'm a superhero, but most of are not. If you try to increase the distance coverage to keep relaying this information, unfortunately, sometimes we need some additional help, perhaps even involving another species. If you want to maintain the real-time nature of information transfer, we have to rely less on our ears and more on our eyes. How do we do that? We just need to change the way we transfer the information. We need to code the message into some sort of code, be it Morse code or somewhere else. And then we have to transmit the signals, maybe using smoke patterns or even light signals or semaphore, so that the receiver can receive that and decode it back to retrieve the original message. This is, of course, fantastic. However, we have some downsides. For instance, you need to have supervision. You need to have this bionic vision, because sometimes the distance that you need to cover for your eyes to see that might be a couple of kilometers. You also rely on friendly atmospheric condition. If it's raining, you won't be able to see or transmit the signals. Fortunately, the next logical step that was invented by our ancestors was also quite inspiring. What if you don't need to worry about transmitting the signal what if the receiver doesn't need to worry about trying to get the signal from the transmitter? What if the signal itself is beamed onto the receiver? This is pretty much the idea of the device called Heliograph. A powerful and focused ray, typically from the sun, is reflected by a mirror and modulated by your coded message so that it can be projected to a spot near the receiver. The receiver then can perform the same usual step of decoding it to receive the message. But decoding Morse code is not fun. This is why about 130 years ago, Alexander Graham Bell, best known for his invention telephone, came up with the idea called Photophone. Photophone works exactly like telephone, except that it doesn't use electrons running on copper wires. Alexander Graham Bell managed to send his voice over a distance of several hundred meters by taking that ray from the sun and then have it modulated by his voice and then retrieve at the receiver and decode it back. This is quite an achievement if you think about this. This is 1880, right? That's 130 years ago. Transmitting voice with light over distance at that time was quite profound, was quite amazing. But we know his other invention better, the telephone. We never heard about this. According to him, this is his best invention ever. If it's not for his wife, he will have named his second daughter after it. Again, we have some constraint with any kind of free space optical communication. The first one is line of sight. You can only transmit in straight lines. It might work on certain open areas, but it might not work if you need to transmit information from one city to another or through mountains. And then, again, the medium that we have, the air, is extremely lossy. You won't be able to send the beam over a great distance. No wonder that electrical communication at that time took over the world by storm. And then people start to use radio and telegraph and telephone and so on and so forth. It wasn't about until 50 years ago that finally optical communication started to gain traction again. And this is because of two factors. One is because of the invention of laser. If you're into comic books, this is how laser is depicted in comic books, a powerful weapon. But in our day-to-day life, we don't use laser that way. We use laser as a sort of light. Why is that? Because the light coming from laser has two distinct characteristics. The first one is highly monochromatic. Every single light source has its distinctive frequency. If you pass it through a prism, there won't be any rainbow behind that prism because it's a single solid frequency. The second one, it is also coherent. All the rays travel at the same speed. They never cross each other. We're going to see how these two behavior will be extremely beneficial when you try to build or when you start to use laser for optical communication. The other great invention is this optical cable or fiber optic. It's made out of silica. It's very lightweight. It is tamper resistant. There's no chance of electric and power interference. And in pretty much every aspect, it is much more superior than copper wire. If you cut the cable, it's going to look like this. The jacket and the buffer are there for protection, but the magic happens inside that thin strand of the core. It's only 8 microns. The thinnest part of your hair is already 16. This is half of that. Because of the differences in the refractive index between the core and the cladding, this creates the optical phenomenon called the total internal reflections. What does it mean? It means that if you launch photons into those 8 microns of silica glass, they get trapped there. They won't go anywhere. This is very powerful and very, very profound as a medium of transmission. Even better, although it's lossy, the medium, this fiber optic as a medium, is very fantastic because you can send the photons inside the fiber optic glass, and then it can travel more than 100 kilometers and then still retain 1% of its power. You can't do that with optical wires, with copper wires. Why is it fantastic? Because with today's modern sensitive optical receiver, you just need that 1% remaining power to be able to recover the complete signal that you send at the transmitter. No repeater is necessary, no power is necessary as well along the transmission cable. This is why the undersea communication channel is mainly fiber optic, right? It's down there, it's under the ocean. Nobody needs to repair it, nobody needs to supply any power. And then it can travel a great distance. In fact, we won't have our job right now doing software engineering and software architecture without all these fiber optics all over the places. There are these tiny little tubes. So if you say that internet consists of many tubes, there's some truth to it. Now, if you look at the fiber optic cable, let's pick one channel, right, from Europe and the US. The total capacity is 3.2 terabyte. It consists of several routes and several cables with the baseline capacity or bit rate of 10 gigabit per second. If you want to imagine 3.2 terabit, it's like a stack of 8 Blu-ray discs. Imagine if you rip the content of those discs and you can transmit that in just 1 second over the ocean. That's how much the capacity is. But one of the nice things about light is that you have so many characteristics of light that you can, typically coming from a laser, of course, that you can modulate. The typical things that we know is amplitude modulation and frequency modulation from the days of AM and FM radio. But you can also manipulate the phase. And this is very crazy because it's so hard to do. But with modern technology, if you do that, the outcome will be amazing. Why is that? Because you can improve the efficiency. Or said another way, if you want to keep the efficiency the same, then you can double the transmission capacity, or you can even quadruple the transmission distance. It's hard to do, but when you get it right, the reward is amazing. This is another thing that you could do with a single optical fiber cable, right? Because with the same physical medium, you can launch 4 different frequencies, each modulated separately, and then you turn it into the optical multiplexer, send it over the same cable, and at the other end, you just demultiplex it and get the original for a frequency. As long as you keep the frequency spacing correct, there won't be any interference at all. This diagram illustrates 4, but today, typically people launch 40 different frequency or channels into the same cable. No need to upgrade your physical medium, but suddenly your transmission capacity is not only double, it's multiplied by 40, or even 100, or even 150. But as soon as you try to get into this extreme, you're just going to face some physical limits. These are some of the optical impairments that we start to see as soon as we start to try to push the limit of the capacity. But rest assured, there are so many scientists, physicists, material science, and other people working very hard to solve this problem. And we start to see the outcome as well. I mentioned about the fiber optic cable between Europe and America, North America. The base is still 10 gigabit per second, but today people deploy 10 gigabit per second, right? Multiplied by so many different multiplying factors due to advanced modulation format, and then so many frequencies that you can launch to a single fiber. The capacity is just amazing, 7.2 terabit per second. Right? And then you double it again to 200. This is also quite astonishing that we can launch and we can transmit so much information in just 1 second. A few years ago, I heard that with the change in the material, finally you will be able to break that barrier even further. It's still an experimental stage, transmission over 1 kilometer, but it's 255 terabit per second. If you have this bandwidth capacity, you can watch the entire Netflix in your lifetime. You won't be still finished because it's so much. Now, I want to use this as a reminder, right? Because if you know somebody, a friend, acquaintance, a family member who is working as a scientist, please give them a hug, a big hug. This is very important because in our line of work, we sometimes feel that we are the best, we're entitled, we do crazy things, and therefore we know everything. It is not true at all. We can do our work, we have our job today. It's because we stand on the shoulders of the giants, the men and women before us. It is therefore in our best interest to show our gratitude, to be thankful, and to stay humble. Thank you very much.